a machine is perfectly aligned during installation, but after startup, vibration increases, seals fail, and the coupling gets damaged. Why does this happen? Because alignment is not static, it changes during operation. In this video, I will explain thermal growth, soft foot, and the correct alignment strategy that every engineer must understand. Slide 1. Alignment is not static. Many engineers believe that once a machine is aligned, it will remain aligned. But in reality, rotating equipment operates under changing conditions. As temperature increases, components expand. The foundation may settle over time, piping can apply external forces, and vibration can continuously affect machine position. So alignment is not a one-time activity. It is a condition that changes from cold installation to hot operation. Slide 2. Thermal growth. Thermal growth is the expansion of machine components when temperature increases. All metals expand based on temperature, and even a small temperature rise can create measurable movement. For example, if a motor pedestal is 1 meter high and the temperature increases by 25 degrees Celsius, the vertical growth can be around 0.3 millimeters. This small movement is enough to create serious misalignment if not considered during installation. Slide 3. Types of movement. Thermal movement can occur in different ways. The most common is vertical growth, where the machine expands upward. There can also be axial growth along the shaft direction, and angular shift when different parts of the machine expand unevenly. These movements change shaft alignment during operation. Slide 4. Cold vs hot alignment. Cold alignment is performed when the machine is at ambient temperature during installation. Hot alignment is the actual condition when the machine is running at operating temperature. The goal is not to achieve perfect alignment when the machine is cold. The goal is to achieve perfect alignment when the machine is hot. So during cold alignment, we intentionally apply offsets to compensate for thermal growth. Slide 5. Estimating thermal growth. There are different ways to estimate thermal growth. The best source is OEM data provided by the manufacturer. If that is not available, you can calculate growth using material properties, machine dimensions, and temperature difference. You can also use plant experience or measure actual growth after startup. Accurate estimation is critical for correct alignment. Slide 6. What is soft foot? Soft foot is a condition where one or more machine feet do not sit properly on the base plate. When bolts are tightened, the machine frame gets distorted. Even a gap as small as 0.05 millimeters can cause internal misalignment of bearings and seals. This leads to vibration, leakage, and premature failure. Slide 7. Types of soft foot. There are 3 main types of soft foot. Parallel soft foot occurs when a foot is at a different height and needs shimming. Angular soft foot occurs when the foot is tilted due to improper shims. Induced soft foot occurs when external forces, like piping stress, pull the machine out of position. Each type must be identified and corrected before alignment. Slide 8. Consequences of soft foot. If soft foot is not corrected, it causes serious problems. The machine frame gets distorted, bearings become misaligned, seals start leaking, and vibration increases. Even a very small soft foot condition can reduce bearing life significantly. That is why soft foot correction is always the first step before alignment. Slide 9. Alignment strategy. A proper alignment strategy follows a sequence. First, ensure the foundation is stable. Then correct any soft foot condition. After that, perform rough alignment. Then apply thermal compensation. Finally, perform precision alignment. Skipping any step will lead to incorrect results. Slide 10. Alignment process. During detailed alignment, you must first confirm that the foundation is fully cured and stable. Then check and eliminate soft foot using dial indicators. After that, bring the machine into rough alignment. Next, apply thermal offsets based on calculated growth. Finally, perform precision alignment using laser tools. After piping is connected, alignment must be rechecked because piping stress can move the machine. Slide 11. Final verification. After completing alignment, always verify conditions again. Check alignment after piping connection and after initial startup. If the movement is beyond acceptable limits, piping must be corrected. Never rely on coupling flexibility to absorb misalignment. That will only transfer stress to bearings and reduce equipment life. Slide 12. Common failures. Some common mistakes include ignoring thermal growth, skipping soft foot correction, aligning before grout curing, not rechecking after piping, and relying on coupling flexibility. These mistakes are the main reasons for coupling failures and vibration issues. Slide 13, Real Case Study. In a real case, a motor and compressor were perfectly aligned during installation. However, thermal growth was not considered. When the machine reached operating temperature, the motor expanded more than the compressor, creating a misalignment of about 0.5 millimeters. This caused coupling damage and increased vibration. The correct approach would have been to intentionally offset alignment during installation. Hack Slide 14, Final Takeaway. Remember these key principles. Thermal growth always occurs, so alignment must compensate for it. Soft foot must be eliminated before alignment. Alignment must be verified after piping connection. And most importantly, perfect cold alignment does not mean correct alignment. The goal is perfect alignment during operation. If you want to become a strong rotating equipment engineer, you must understand real-world behavior, not just theory. Like this video, subscribe for deep engineering knowledge, and comment "Align" if you want real failure case studies. See you in the next video.